Hey guys, and welcome back to another video. This is Insertion Sort, and we're going to be understanding what in the world is Insertion Sort and how does it differ from other sorting algorithms that we discussed earlier. Well, as the name suggests, insertion is what is going to happen, but not really. It's more like transfer and then insertion. Anyways, let's start with it. Okay, so let's take an array like this: 5, 4, 1, 2, and 3. Okay, so there's going to be two parts of this. There's going to be a sorted section and an unsorted section. When you say sorted section, it's not like this 5 is in its correct position. There is only one element which inherently is sorted despite whatever the number is. If you were to just consider this part of the subarray, right? So this part of the subarray is sorted, and there's only one element as of now, which is 5, and that's okay. And this part is unsorted, right? So that's what we're going to deal with and how this sort of thing resolve. Okay, so we're going to maintain two pointers like many other sorting algorithms that we did. So we're going to define I starting from 0, first index, okay? And if in case you just are wondering about indices, these are the position inside an array, and the size of the array is going to be sorry, the indices in a size of n would be from 0 to n minus 1. Anyways, so I is going to start from 1, and uh, I is going to start from 1, and you're going to maintain another variable called j that would be one lesser than I. That is where it's going to start. Okay, so j is going to be I minus 1. Okay, cool. So what is going to happen in insertion sort? Exactly. Okay. So we're going to maintain this guy, which is the very first iteration. So this part would be your key because you're trying to find amongst this array of sorted section, you're going to find the deservant position, maybe not the deservant index as of now, because you're only considering this part of the subarray, right? So you're going to find the deservant position of 4 over here. Okay, so now it's going to be a little hard to explain for the very first example, but you would understand that in the very second iteration. Okay, so if this element is greater than 4, which is key. I'm going to store key as 4. I'm going to tell you that why I'm doing that. So I'm going to not swap, but push 4 over here. Because the goal is to place 4 in the sorted section, but like inserting over there. So I'm going to insert 4. So now, okay, this is minus 1. Can I insert over here? If you know about arrays, you can't really create an extra index or attach an index extra and then say, I'm going to insert 4 over here, and that's going to have an index of minus 1. Well, surprise, surprise, you can't do that in computer science or in the concept of array. So what you would have to do is inherently place it before 5, but you would also have to push 5 over here. So since when I push 5 over here and then overwrite it, the value of 4 would be vanished. That is why I already stored the value of 4. Now I know the value of key that is deservant of this position over here. I'm going to replace that over here. Okay, if you didn't understand that, it's okay. The next iteration is going to make you much more clear. So now what happened is basically swap happened. That is what I could say. You might say, hey, it's like bubble sort, we're swapping. No, we're not swapping exactly, but we're pushing elements to the right as long as they're greater than the key. And okay, so this is 4, and what is the other elements we had? We had 1, we had 2, and we had 3. Okay, so let's get our indices right, which is 1, 0, 1, 2, 3, 4. Okay, so now the sorted section would have moved a little bit this side. So right, So that's your sorted section, and this is your unsorted section. And now what happens is you'd have to consider something like this, and this is going to be your key, because after all, what you're going to do is insert it somewhere and go about pushing all these elements to the right. Okay, so that is what you're doing. And this position could either be at the end, and as I said, it couldn't have been -1. You can't really do that. Or it could have been somewhere in the middle as well. That is a possibility that could have happened. And maybe in the next iteration that can happen. Okay, so I'm going to push 5 and 4. But before that, since when you push elements or override elements, the value of those elements, so those values would be lost. So that is why I'm going to store the value of this key, which is array of I, as this way. Okay, so your key is stored, I'm sorry, which is inherently means your key is now 1. Okay, that's great. Well, the next part of this is to push elements as long as they are greater than key, which is 1 in this case, right? So we have 4, we have 5. Is 5 greater than 1? Definitely it is. So that's going to be, these are some intermediate steps. So these are not exactly iterations. And this is amongst the same first, second iteration. Okay, so do not get confused. And once that's done, and you're going to see if 4 is greater than 1, it is. So 4 is going to be present here, and there's going to be 5, and there's going to be 2, and there's going to be 3. Okay, so this sort of intermediate step is going to be there. Now, what you're doing inherently is moving this J pointer every single time. So what you were doing was maintaining a J pointer over here, and then moving leftwards, which means doing J minus minus, right? So your pointer was moved over here, so you compared with 4, it was also greater than 2. Sorry, greater than 2. So you also put the value. Oh, sorry. Confused. Yeah, so it's right. So you also put the value of um, 4 over here. Now, this 4 is actually the correct position. 2 is deserving to be put into, because 2 is looking to be in a position where it's in a correct position of this sorted space, which is 4 and 5. And 2 is looking to be in its correct position, which is 2. So it wants to be ahead of these guys, right? So that is what it was doing. So I had to push 5, I had to push 4, and then I'm going to bring in 2. So now where the J pointer would have gone is over here, which is at -1. So I'm going to do J plus 1, array of J plus 1 is equal to key. Why J plus 1? Because it's going to go to this index, which is 0. And then it's going to overwrite this value to be 2, because this is the previous value of 4, and now it's 2. So now how does the array look like? It looks like this. It is 2, 4, 5, and sorry, okay. So our key was 1. I am so sorry. I'm so sorry. Our key was 1. Our key was 1. I'm so sorry for that. So our key was 1, right? So now 1 is in its proper position, and now we have the remaining elements 2 and 3. So, okay, so this is a different case or scenario, which you probably expected to see. Whoa, I'm really bad at that. Aren't I? Aren't I? Okay. So now this is your sorted section. Okay, and this is your unsorted section. Well, technically it is sorted, but it might have not been sorted in many of the cases. So now we have this element, which is 2, which is going to be your I. Okay, I'm going to store the value of key to be array of I, which is 2. Right, and now I'm going to try to store this in its correct position. If you look closely from the sorted section, 2 deserves to be in middle of 1 and 4, right? You can't place, hey, the index is 0, 1, 2, 3, 4. I can go by placing it 0.5 so that I can place it in the middle. You cannot create indices of something of that fractional value. Okay, you cannot do that. But what you can do is probably push 4, 5 to the right, 5 to the right, and then 4 to the right, and then push 4 over here. Since when you push 5 to the right over here, the 2's value is going to get overridden. That is why you maintain a value, a variable called key where you store the value of 2. Okay, cool. So now let's do it. This little tiny intermediate steps that we do. So we have 1, we have 4, we have 5, and is 5 greater than 2? It is, so that it's going to be moved to the right. And then we still have the value of 2, so it's not really lost. And now we're going to compare, j comes over here, j was over here, so j is now here. So j is going to compare with, array of j is going to be compared with key, which is greater, so that also has to be moved to the right. So I'm not going to write it here because it's going to be confusing for you. So 4, 4, 5, and 3. Cool. And now j is going to go here. And j is going to compare array of j. Is it greater than key? Well, it's not. So that means probably the next position is where the key deserves to be placed. And that is array of j plus 1 is equal to k. And you would have to break your loop before that, your while loop. Okay, and then come out of this. So technically what would happen is to place 1, 2, 4, 5, and 3. Cool. Now in this position, you can probably do the same thing with 3 and then try to place it over here, push 5 forward, rightwards, 5 rightwards, and then place 3 over here. You don't have to touch any of these things. You would probably have j present over here, and then you should do j plus 1, and then that's going to be your key. Assign that with key value. Okay, so that's more like it. And let's try to write the code for this whole thing. And starting off, what did we do? We started off our iterations with I being from 1. I was equal to 1, right? And slowly we went to n minus 1. So that is what we did. So we're going to write a for loop starting from I is equal to 1 to n minus 1. Cool. All right. And then what did we do? We had okay. So we also defined key first, right? Key is equal to array of I, right? And then what did we do? We defined the value of j, which is I minus 1, right? Which is 1 lesser than I. This is, right? So this is what happened, and now while j is greater than or equal to 0, because if it was lesser than 0, how could you even indice that? If you did array of minus 1, you would get an index bound error. Okay, so once this check is done, then you can say if array of j is greater than key, because it has to be greater, only then you can push to the right. So that is what you're going to do, right? And then you're going to do array of j plus 1 is equal to array of j. Okay, and also you're going to have to move this pointer towards the left, and then at the very end, you're going to do j plus 1, okay? Just like in this position, j would have come here, and then you would have to place at j plus 1 is equal to key. Cool. So I guess that's it, and that would do the things for you. Well, anyways, now let's try to code this thing up. Okay, let's try to solve this problem. And we have an insertion sort, right? So technically, what do we have to do first? We already have n, so I'm going to start writing the code. For I is starting from 1, so is lesser than n minus 1. I mean, as long as it's equal to n minus 1, so it's lesser than 1 is also fine. So I plus plus, and then I'm going to define int key is equal to array of I, and then int j is equal to I minus 1. While j is greater than or equal to 0, and if array of j is greater than key, is that as long as that's true, array of j plus 1 is equal to array of j, which is basically move this element to a position or index plus 1 of that, right? And then also you have to move your j towards the left. So that is what you do, move the j pointer. So this is a while loop that keeps happening, right? And then after all of that drama, you just have to move j plus 1 to, place your key at j plus 1, because most of the times it would just go to minus 1 and then you would have to do plus 1 to place your element, or maybe it may be somewhere in the middle and then you would have to find j plus 1 and place your key because your pointer would have moved a little bit left. Anyways, let's try to run that. So all of our test cases have passed, but let's try to submit because there might be large test cases that could fail. Okay, so we have solved this problem, and so that was insertion sort for you guys. And let's talk about the time complexity and also the space complexity of this. So so time complexity, right? So wait. So there's a for loop for sure. So there's a for loop that runs for n times, right? So, and then there's a lot of these operations, and then you would have to multiply with n with something, and then plus n with something, okay? So instead of that, if you just consider what's really happening is in this array, let's take worst case now, okay? Let's try to find the worst case first. So let's take an example like 5, 4, 3, 2, and 1. So what's happening over here? So you just have one element, and then you know that you just have to do one operation to just go about pushing this over here and then do this. So that's going to be one operation. Okay, cool. Okay, this is your worst case because all of these elements are sorted in a descending order. So 5, 4, 5, 3, 2, and 1. Cool. And now you have 3 is this, so you have to move like 5, you have to move 4, and then you have to put 3. So you have two operations here. Technically 3, but even if you write that, what you can observe over here in the next iteration at least is it's going to be 3, 4, 5, and then 2, and then this is your place where you do all that stuff, and then you push 5, and then you push 4, and then you push 3, and then you push 2 to this position. So around three operations, right? So what you can see is what's really happening is 1 plus 2 plus 3 plus, as long as it reaches n minus 1, and that's equivalent of n into n plus 1 divided by 2, sum of natural numbers. So that's around n squared by 2, or equivalent of n squared. So that's your worst case for insertion sort. And okay, so that's worst case is O of n squared. Now let's talk about average case. This is best case. This is this is worst case. Now let's talk about best case. Then we'll talk about the average case. So the best case is gonna be okay. Let's just take this array. 1, 2, 3, 4, and 5. So you'd have to do this. You see that it's already proper, so you don't have to do anything. So then you go for the next iteration, and you already see that it's proper. You don't have to do anything. You have to go to see the next one. There's nothing to be done, and so forth. You see that you actually never enter the J loop because that's never true. Array of J is never greater than key in the best case, okay? Or at least in one of the better cases, but in the best case, J is never entered. So the only thing that has entered is the I loop, which happens 5 times or n times, right? So that is your best case. So that is your best case. And your average case, of course, would have been average of this, which would be around O(n) square itself. Okay, you can just try to solve a bunch of these things. And let's talk about the space complexity. And alas, the space complexity is going to be 1. Why? Because we don't really use any extra space. All we did use is an extra variable, which is key. I mean, even if you did use like 5 or 10 variables, even if you said it's O of 10, it's almost equivalent of saying O of 1. Because when you compare something like 10, it should be comparable to n, how the size of the array. Because size of the array, when you compare it in terms of time complexity, you always think of numbers something big as 10 power 5 or 10 power 6 or such huge million numbers. We don't really care if it's 10 or 20 variables, because when we do compare it, it's comparable, it should be comparable to the n value. Because n, when we try to equate it, when we try to find complexities, let's say for something like O of n squared, it's usually done in terms of n being 10 power, let's say 10, and that would have been 10 power 20, for example, right? So in a similar way, we have not really used anything, so space complexity is O of 1. So that is your space complexity for insertion sort. Well, I hope you guys enjoyed this video and found it informative, and the next video is going to be merge sort.